Predicting the future is difficult at best. At the beginning of the 1900s, many people thought that all of the basic laws of nature had been discovered, and all that remained was tying up loose ends. Then came the airplane, Einstein's theory of relativity, quantum theory, subatomic particles, rocket technology, helicopters, jet engines, space flight, penicillin, radio and television, electron microscopes, computer technology, sonar, radar, lasers, and of course, silly putty. What more could the future of chemistry hold? Currently, there are many new ideas in the research and development stage, and we are going to look at some of those. But some technologies just seem futuristic, regardless of their age, and no technology fits that description better than nuclear energy. Just the word nuclear sounds futuristic, but incredibly, nuclear technology is older than color television. But what exactly is it, and how does it work? We've already seen that all elements heavier than lead and bismuth are radioactive. The elements break down and decay. With some elements, by forcing a neutron into their nucleus, they get very heavy and start separating or decaying into more stable elements. Uranium has three isotopes, 238, 235, and U-234. Here's the percentage of how much of each one is in natural uranium. Over 99% of all uranium is U-238, which is why the average atomic mass on the periodic table is listed at 238. Only 0.711% of all uranium is U-235, and this one isotope of uranium is unique in its abilities and even its availability in nature. Uranium isotope number 235 will accept a neutron and immediately split into lighter elements, typically into barium-141 and krypton-92. In addition, U-235 will release the binding energy that held it together, and of equal importance, it will throw off neutrons of its own. Those neutrons will in turn strike other U-235 atoms, which will split, release their energy, and throw off their own neutrons. This is fission. Fission is a term coined by none other than Lise Meitner, and it all happens in under a fraction of a second. Under the right conditions, this reaction can either be carefully controlled or left to run out of control. Reactors like this represent controlled fission in order to make electricity, and it works something like this. The objective is to turn an electric generator. Water runs through yards of pipes crammed inside of a furnace. The furnace is heated up, boils the water inside the pipes, and the water turns into steam. Steam violently expands over 600 times and is forced over the fans of a turbine. This incredible steam force turns the turbine blades, which in turn turns the central shaft, which is connected to the electric generator. Around the generator shaft are very large magnets that spin inside a very large coil of copper wire. This rotating action produces electricity, which is sent over transmission line wires. Now, hydroelectric dams channel water down tubes that blast into the turbine blades and spin the generator. No fire needed. But otherwise, you need steam to turn those turbine fans. And the question is, how do you boil the water? Well, in conventional power plants, coal, gas, and oil are commonly used as the fuel to heat the furnace and to boil the water. Just like the old steam engine trains used coal to heat the furnace that boiled the water that pushed the train wheels. Same principle. Burn the coal, heat the water, spin the wheels. Solar power can be focused onto the water tubes, and that will boil the water using the sun. And you can boil the water using the controlled reaction from a nuclear reactor. A reactor is almost exactly the same as our steam engine model, except for the fuel. Natural uranium contains only 0.711% of U-235. By enriching the uranium, the fuel for reactors now contains about 4% U-235, and highly enriched uranium, called weapons-grade uranium, is saturated with about 90% U-235. Each reactor-grade 4% U-235 fuel pellet is only slightly radioactive, but just 8 of them provides enough energy to power an average house for a year. The pellets are sealed in metal tubes, and several thousand of the metal tubes are placed in the core of the reactor. As the uranium deteriorates, the bundles begin to heat up. Now for the steam. The most common design for commercial reactors is the pressurized water reactor. There are 3 separate water loops to make this happen. Water loop number 1 absorbs the heat from the fission of the uranium and is under pressure so it doesn't turn to steam yet. This pipe goes into a steam tank, transferring the heat again into water loop number 2. Loop number 2 turns into steam and drives the steam turbines to make electricity. The radioactive water never touches the turbines. Loop 3 takes cool water from a nearby lake and cools the steam from loop number 2 back into liquid water. In fact, the clouds you see rising from cooling towers is the lake water vapor from loop number 3. This, in essence, is how a nuclear reactor turns water into steam. The blue glow you often see in pictures of reactor water is called Cherenkov light and is a byproduct of the nuclear fuel reacting inside of the water of loop number 1. Now, the fuel pellets can produce way more heat than the water can possibly take away. So how do you keep it from overheating? Fortunately, some elements, like boron, have the unique ability to absorb large amounts of neutrons. So if you absorb all the neutrons in a U-235 chain, they can't run into other U-235 atoms, and the reaction slows down or stops altogether. So, control rods made of boron or similar elements are inserted into the reactor, absorbing neutrons and preventing it from overheating. The control rods will automatically drop into the water in the reactor and stop the reaction if it begins to overheat. Unless, of course, you bypass all the safety controls, which is ultimately what happened in 1986 at the Chernobyl reactor in the former Soviet Union. In order to run an experimental test, nearly all of the safety controls were intentionally bypassed. Well, the test went bad, and with all of the safety controls off, the reactor steam built up enormous pressure, and before the situation could be made right again, the steam exploded out of the reactor, resulting in the first Level 7 incident on the International Nuclear Event Scale. So, given that you don't bypass all the safety controls, a nuclear reactor is simply a glorified steam engine, all using the controlled reaction from nuclear fission. On a winter's day in December 1951, the world's first peacetime use of nuclear power happened in the isolated flat expanse in Arco, Idaho, when these 4 light bulbs were lit using power from experimental breeder reactor number 1. And today, 80% of France's electricity is from nuclear energy. In Switzerland, it's 40%, Germany 30%, Japan 25%, and in the United States, 1/5 of all electricity is produced from nuclear power. That is controlled nuclear fission. But what if the fission reaction is intentionally left uncontrolled? In July 1945, in the desert of Alamogordo, New Mexico, they did exactly that for the very first time. The US government hired this man, Berlin Brixner, to shoot movies of the test in 16mm black and white film. It would be an explosion beginning with the brightest flash ever produced on Earth. Brixner later said, "There was no sound. It all took place in absolute silence, and I was just spellbound. Then it dawned on me. I'm the photographer. I've got to film that ball of fire." And he jogged the camera up, capturing this image. But as we mentioned, the uranium must be highly enriched until it reaches weapons grade, about 90% U-235. And you have to have a big enough chunk of U-235. If it's too small, the neutrons will all simply escape out and nothing will happen. But if you have about 15 pounds of weapons grade U-235, about the size of this billet, you can achieve critical mass and sustain the atomic chain reaction. And the simplest way to start the chain reaction is to take a small bullet-sized piece of the U-235 and fire it at the remaining chunk. An explosive fires the bullet down a barrel, which strikes a sphere of U-235. The chain reaction itself is over in about 500 billionths of a second. This was the type of device, codenamed Little Boy, that was dropped on Hiroshima in World War II. It was the first use of nuclear power as a weapon of war. Less than 2% of the U-235 is fissioned before the bomb destroys itself and the reaction stops. Now, this is a ring of almost 100% pure plutonium-239. The first plutonium-239 was made in the nuclear reactors at Hanford, Washington. It is much more difficult to produce and is much more powerful than uranium-235. This type of device uses a sphere of explosives to compress the baseball-sized plutonium, thus initiating the chain reaction. The yield from plutonium-239 is about 22,000 tons of TNT, and nearly 20% is fission before the device disintegrates. It was this type of device, codenamed Fat Man, that was dropped on Nagasaki 3 days after Hiroshima, thus bringing an end to World War II. The other nuclear term we hear about is fusion. Fusion is exactly the opposite of fission. Fission takes the heaviest elements down here and splits them, releasing energy. Fusion, on the other hand, takes the lightest elements up here, 2 isotopes of hydrogen called deuterium and tritium, and crams them together, fuses them, fusion. And if you jam 2 protons and 3 neutrons together, you make a helium atom and an extra neutron, plus a ridiculously powerful burst results from the fusion. On Earth, it is very hard to fuse 2 light hydrogen atoms. You can't just push 2 positive protons together because, as current atomic theory recognizes, they repel each other fiercely, just like magnets. The fusion of atoms happens only at very high temperatures, in the millions of degrees, which overcomes their natural repulsive action. Once 2 atoms fuse, the resulting heat energy causes other hydrogen atoms to fuse, and the chain reaction begins. But on Earth, these incredible temperatures exist only in tightly controlled laboratory experiments and in atomic bomb explosions. Knowledge of this resulted in the first fusion bomb, also known as a hydrogen bomb, also known as thermonuclear weapons. A fission bomb is used as the trigger to detonate the hydrogen bomb. The explosion is used to compress, heat, and detonate the hydrogen material. The first thermonuclear bombs were tested in the early 1950s on islands in the middle of the Pacific Ocean. These fusion weapons were not measured in kilotons, thousands of tons of TNT, but in megatons, millions of tons of TNT. The results were apocalyptic, to say the least. The Comprehensive Nuclear Test Ban Treaty bans all nuclear explosions in all environments for military and civilian purposes and is the most far-reaching attempt to ban nuclear weapons. It is yet to be agreed upon by all nuclear-capable nations. On the other hand, controlled fusion technology offers tremendous energy potential for the future. Fusion power, or controlled fusion, refers to the potential commercial production of usable power from fusion. Controlled fusion is still very much in the research stage, and if successful, the heat generated from a sustained controlled fusion reaction would simply be used to, once again, boil water and drive a steam turbine. The same way we use controlled fission today, but without the radioactive waste. Remember that it requires tremendous heat to fuse hydrogen atoms. Controlled fusion attempts to generate that heat in a tightly controlled laboratory environment as opposed to using nuclear explosions. One promising method is to use high-intensity lasers. A focused laser can generate the needed heat and is focused on a tiny target of encapsulated hydrogen, with the hope of creating a controllable chain reaction of fusion. One example is at the National Ignition Facility at the Lawrence Livermore National Laboratory in California.
Starting countdown for a shot on my mark. 3, 2, 1, mark. Clock is running. 5, 4, 3, 2, 1, shot.
If successful, this tiny hydrogen fuel pellet would sustain a chain reaction of ongoing fusion, making enough heat to boil water and drive a steam turbine, thus producing electricity. A completely different type of fusion laboratory are called tokamaks, a Russian acronym meaning donut-shaped chamber with magnetic coils. A tokamak confines the hydrogen in a magnetic chamber, heating it to 200 million degrees, more than 10 times the theorized temperature of the sun's core, in order to try and sustain fusion. ITER, the International Thermonuclear Experimental Reactor, is an international tokamak under construction in France. When completed in 2018, it will be the largest tokamak fusion generator in the world. There is almost no radioactive material and minimal risk of a runaway meltdown, since as the temperatures needed to sustain fusion immediately cease if something goes wrong. The primary fuel is hydrogen, and there's plenty of water to supply hydrogen. One bath full of water would supply the total energy needs of a single person for 30 years. Once again, the goal is to create sustained fusion with enough heat output to boil water, drive a steam turbine, and generate electricity. Scientists have been working on fusion for over 50 years. Most scientists think that the first fusion power plant will open sometime between 2030 and 2050. The ultimate goal would be to produce room temperature fusion, often called cold fusion, but this might be generations away. Fusion is very difficult and to date has proved elusive. It is just about beyond our scientific capabilities. It is at the very cutting edge of technology. But fusion also holds potential for providing civilization with a clean and nearly limitless supply of energy. And this brings us naturally to a related technology, also decades old, equally baffling, and yet still futuristic. Particle accelerators, also known as atom smashers. We will look at two areas where particle accelerators and chemistry meet. First, a quest for the island of stability. How is it that we keep finding new elements? It's not like we just dig around the ground and find a new element. You have to add one proton at a time to get a new element. So where do we keep finding all these new elements to tack on to the back of the periodic table? Well, the short answer is we manufacture them in machines called particle accelerators. At least this is how Glenn Seaborg created his new elements in a machine called a cyclotron. So you want to make the next element, say one with 114 protons. You take a metal strip of a heavy element, like plutonium that has 94 protons. That's the gold color target. And you bombard it day and night for weeks with a stream of, say, calcium atoms with 20 protons. That's our purple atoms here. And if you're smart, and if you're lucky, eventually one or two of those atoms will fuse, and 94 plus 20 is 114. Atomic cameras take cryptic snapshots of these results. The lines on these plates are measured and tell the particle energy, trajectory, momentum, and total energy. An element with 114 protons might look like this and will exist for a few milliseconds, literally disappearing in a blink of an eye, and then it is gone forever. Well, then you might be asking to yourself, why bother? If they are gone in a millisecond and gone forever, why go through all the work? Well, nearly all elements up to element 100 are fairly stable. Oxygen, iron, mercury, even uranium, plutonium, and americium. After 100, there is a sea of unstable elements, a sea of instability, where elements are very unstable and fall apart in minutes, or seconds, or millionths of a second. This is every element after 100 or so, but calculations suggest that somewhere out here is a section of stable elements, an island of stability, where some heavy elements might not decay so quickly and will stick around for a few days or months, or maybe indefinitely. Elements 120 or 126, or even 184, are possibilities. If the island exists, and if the elements will stick around long enough, and if you can manufacture enough quantity of them, and I realize that's quite a few ifs, well, maybe you can get something like a new metal, or a new noble gas, or even something like transparent metal, or how about a liquid that will conduct electricity at will, or maybe even something that will defy gravity. That is one use of particle accelerators, the quest for the island of stability. Particle accelerators are actually quite common. In fact, the good old cathode ray tube, like those found in older television sets, are a type of particle accelerator. As we saw earlier, electrons are accelerated from the cathode end and speed toward a phosphorus screen, and when they smack against that screen, it causes a little spark of light. Aside from simple cathode ray tubes, the worldwide inventory of particle accelerators is about 15,000. Most are smaller and are used in medical applications to treat certain cancers, or used in industries to build silicon chips. But some of them are huge, and they're used to smash atoms to bits in order to find out how they're built. This is very much like trying to determine how your computer is designed and built by examining the pieces and parts after you've thrown it off of the Empire State Building. And this procedure is done with a different kind of particle accelerator called a super collider.